Welcome back to the fourth lecture in this series on concurrency, state models, and design patterns. Today we're going to start looking at design patterns dedicated to ensuring safety in concurrent programs. The outline looks like this for today. First, we'll have a brief overview reminding us the difference between idioms, patterns, and architectural styles. Then we're going to have a look at 4 general design patterns and an additional mechanism for ensuring safety. We will see that immutability is one of the most basic design patterns for ensuring safety, which is often forgotten, but it can actually be applied in a lot of interesting situations. Then we have full synchronization, just using the synchronized keyword and without any waits and notifies, which can be used in certain situations but has some limitations. Then we have partial synchronization, where we restrict synchronization to certain critical sections. And finally, we'll have a look at containment, where objects are not exposed to concurrent threads, but are passed back and forth between containers which themselves are concurrently protected. Finally, at the very end, we'll have a brief look at transactional memory. So first of all, let's remind ourselves the difference between idioms and patterns and styles. Idioms are, as the name suggests, idiomatic usages, which are fairly specific typically to certain programming styles or programming languages. So they're fairly low-level implementation techniques, typically specific to a particular programming language or style. So things like futures, remote procedure calls, function objects, these are what we typically think of as being idioms. Second of all, we have design patterns, which are recurring solutions, design solutions to problems that occur over and over again. We know these from the original design patterns book by the so-called Gang of 4 back in 1994. And we will see that in the area of concurrent programming, we also have design patterns which are designed specifically to address the problem of concurrency problems in concurrent programming. Design pattern is different from a component or from an idiom in that it's a general design solution which tends to be programming language independent. So even though we are working here in Java, the solutions that we are using can be applied in many other programming languages, perhaps using somewhat different mechanisms. But the underlying ideas, these patterns, can be applied independent of the Java language. Finally, we also have architectural patterns or styles, which occur at a higher level than a design pattern. So whereas a design pattern is solving a particular design problem in a part of an application, it's kind of a mini architecture, which only affects that part of the application and not others. An architectural pattern is something which runs through and affects the design of the whole application. So it provides you guidelines with which determine what all the components of an application, what roles they play. So data flow and Blackboard are examples of architectural patterns, but an even more simple and fundamental one is client-server. So client-server architecture splits a concurrent, in fact a distributed application, into at least 2 parts. So there are parts which are dedicated to the client, and there are parts which are dedicated to the server. And the architectural style will dictate how components are distributed in the entire application. So as you see, an architectural pattern is like a design pattern, however it's broader in that it impacts the design of the application as a whole rather than a specific part of it. Now let's start having a look at some specific design patterns which concern safety and how to deal with it in concurrent programs. So the whole problem of safety is making sure that an object doesn't get into an inconsistent state. Well, a trivial way of solving this problem is simply making sure that the object does not change state. This seems like a non-solution, but in fact there are many interesting situations where if you rethink a problem, you can actually ensure safety in a very nice way by making your classes immutable. So the intent is to bypass all these safety issues by not changing an object's state after its creation. Well, when can you do this? Well, in fact, when an object is something that represents essentially a value of a simple abstract data type. So numbers and colors and shapes and things that are entities in themselves but don't necessarily have to change their value over time. Second of all, when the updating by copying is cheap. So a very good example is the string data type in Java. Strings in Java are immutable. So you cannot, once you've created a string, you cannot modify it. The only way you can get a modified value is by creating a new value which is derived from the original one. So for example, you can concatenate hello and the space string and world to get the hello world string. This is not strictly a mutation because you are not modifying any of the underlying strings, you're just creating a new one on the fly. As a consequence, since none of the string objects are being modified, there's nothing that needs to be synchronized. This is a very beautiful and a very elegant solution to the concurrency problem. Obviously, it doesn't apply in all situations, but it's important to be able to recognize when you have a situation when it can be applied. So particularly when you have objects that represent values and when you can cheaply create new objects that represent new values. It may also be the case that you want to separate objects into versions which are immutable and those which can be modified. So this is also the case in Java. There are situations when you would like to be able to incrementally build up a string by adding characters and strings to the end of an existing string. This cannot be done with the string data type, but there is a string buffer data type, for example, which is mutable. And rather, if you have to build up a very, very long string by adding sentence by sentence or word by word, this may cause the creation of lots and lots of intermediate objects, which can have a performance impact. On the other hand, with the string buffer, you simply have a single object where stuff is added to the end, and once you're done, you can say, okay, now convert that to a string for me by invoking toString. So in such cases, you can have as a default the immutable class and then a mutable version of the same class for the situations when you really need to be able to make incremental changes. It can also be interesting if you have a situation where multiple instances really represent the same underlying value. So for example, numbers. 712 is always 712. The color red is always the color red. So you can then think of those as being the same underlying values. Notice here at the meta level, this pattern has a name which is called immutable classes. And in describing the pattern, there are various sections that are important. So every pattern has an intent. That's the problem that it's meant to solve. It has an applicability. Those are the situations in which you can apply it. There may be variants. There may be implementation details. There may be other patterns with which it may collaborate, and so on. Clearly, on these slides, we don't go into all of the details of these patterns, which is why there's a whole book on them, which is the book by Doug Lee that we're referring to in this course. So we're simplifying the patterns by presenting them in just a few minutes and on a few slides, but to be a real design pattern, there usually is a fair bit of documentation that is needed to describe the full design pattern in all its glory and detail. There are some variants of this basic idea of immutable classes, and here are a few of them. One is the idea of stateless methods. So you may have a class that's not fully immutable, but there may be particular methods that don't depend on an object's state, or may depend only on part of the state that does not change. So if you have such a case, then such methods do not need to be synchronized. So I may have an object with a lot of state variables, and some of those may be immutable. If I have methods that depend only on the immutable parts, well, then those are stateless methods. If I have a method as well that does not access the state at all of that particular object instance, I can even declare it as being static. Recall that a static method is one that belongs to the class and is shared by all instances. So that only makes sense if such a method is not accessing any state of the individual object, but only information which is the same for all instances of the class. Another example is that of a stateless object. So this is an object that doesn't really have any state of its own, but that any state that is needed is computed dynamically. And a third case, which is quite similar, is that of hardening. This is particularly the case of objects that are lazily computed. So you may have an object that's created and has a complex state, but only after the first time that it's accessed will its full state be initialized and then no longer change. So this object, after its first access, hardens and becomes immutable after that point in time. So it behaves just like an immutable object. It just can be created very cheaply and quickly, and only when it's accessed does the expensive phase of initializing it take place. There may also be objects that have a mutable phase and then enter an immutable phase. And then in order to take advantage of the immutability pattern, you should expose these objects to concurrent threads only after the hardening phase. So for example, there may be one single thread, one object, which accesses the object during its initial period when it's mutable, and only after that phase can multiple concurrent threads access it. In order to create an immutable class, there are various steps. So we'll see that with all of these patterns from Doug Lee's book. First of all, you should declare a class with instance variables that are never changed after construction or after hardening, as the case may be. Here's a kind of a toy example. We'll see a few of these, and I'll also try and give you some real running examples as well. So many of the examples from the book are toy examples, but they have the advantage of being extremely compact, so you can see in just a few lines of code the underlying idea. In addition, I'll try and show you some slightly larger examples, which will show you in still with toy examples, some practical applications of the same idea. Here's a class that's called a relay. So a relay is simply an object that passes requests on to other objects. The facade design pattern is an example of such a thing. So a facade provides a common interface for many underlying objects which are available elsewhere. So instead of having to know all of the individual objects that you want to access, you simply talk to the facade. And the facade itself has no state of its own, but simply relays requests to other objects. Here's a trivial example of such a facade. It's not much of a facade, it only has one operation, but it has one instance variable called server underscore, and it points to another object. Once it's created, the server variable never changes. As a consequence, the relay object itself is immutable. The server object might be mutable, but that doesn't concern us. So as a consequence, because the relay itself is stateless, none of its methods need to be synchronized. So in particular, the doIt method doesn't need to be. We don't care about the server has to protect itself. Perhaps the server's doIt method is synchronized, or perhaps it's using other design patterns to ensure safety. We don't know, but that doesn't concern us. All that concerns us here is this class is perfectly safe as it's designed here. Next, especially if the class represents an immutable data abstraction like string, you should consider overriding object.equals and object.hashcode. Now, I mentioned earlier, here we're talking about design patterns, not idioms, and object.equals and object.hashcode are fairly specific to Java. However, I argue that this is the same for pretty much all object-oriented languages. Now, this is important. If you look at Ruby or Smalltalk or Python or any language that you will, you'll find similar underlying design principles. Most of these languages distinguish between object identity and object equality. Object identity says two objects are the same. They are the same object. In Java, for example, the equals operator will test if two object references are identical. They point to the same object. And the equals method, which is defined in the class object, its default implementation is the same. It tests for identity. But if you really want to know whether two objects represent the same value, for example, two string objects, they may not be the same object, but they may contain the same set of characters in the same sequence. In that case, the string.equals method must be overridden and re-implemented to test whether the two objects represent the same strings, even though they may be two separate objects. Now, in order for fundamental data structures like dictionaries to work, you also need to make sure that hash code works correctly. In other words, two objects that are equal should always have the same hash code. The default implementation of hash code, however, will not guarantee this. So that means if you change the implementation of the equals method, then you should make sure that the hash code method also is coherent and will give you the same hash code for equal objects. This is usually pretty simple to do, and we're not going to discuss it further here. I only like to point out this is pretty much the same in any object-oriented language. So if you have such a situation where you want to implement some kind of equals method that tests whether two objects have the same value, you have to override that method, and you will also have to override whatever method it is in the system that implements hash codes. Next, you should also consider writing methods that generate new objects of this class. So for example, we want to create new strings, we want to create new colors, we want to create new kinds of complex numbers, as we'll see in a moment. Another thing you might consider, but may or may not be a good idea, is declaring the class as final. When you declare a class as final, that means there may be no further subclasses. So in particular, if you want to make sure that nobody defines a subclass which suddenly is mutable, you may say, okay, this class is final. On the other hand, that's kind of rude to future developers. Maybe a future developer would like to have a subclass which is immutable, or perhaps there's a good reason for having a mutable subclass. By declaring it as final, you exclude that possibility. It depends how important it is for you to have control over this. So you may consider this, but I wouldn't necessarily recommend it. Next, if only some variables are immutable, you can use synchronization or other techniques for the methods that are not stateless. So you may have a class which is partly immutable and partly not, in which case you'll apply a mixture of different design patterns. Here's a little bit more realistic example, and it's a complex number class. So our complex number class has instance variables x and y that we see here. X and y are final. They do not change once they're initialized. So in other words, our complex numbers are pure values. When we create an instance of a complex number, we just initialize the x and y values. Now we have a bunch of operators. We're programming in Java, not in C++ or Smalltalk or Ruby, so we cannot override the plus and times operators, so we have to have plus and times methods. But as you can see here, each of these operators, they do not modify the complex number itself, they simply create a new complex number with new values. This is similar to the idea of the string method, where I cannot modify a string, but I can concatenate two strings together and get a new string. As I mentioned, we have to make sure that the equals method is correctly overridden. So this is an idiomatic way of expressing an equals method in Java, and it's fairly similar in other programming languages as well. The first thing you want to check is whether the other object that you're looking at is an instance of the same class. Because if it isn't, then clearly they're not equal values. Usually that's the case. Normally, it's bad practice to ask an object what type it is, but this is a pretty good counterexample, an exception to the rule, because this is the one case where you want to say, well, only if I know that the other object is the same type as me, then I want to dive in and see whether the values are the same. So, if I see that the other object is an instance of a complex number, then I will downcast it and assign it to an instance variable other, which is of type complex, and then I can actually do the comparison and only return true if we have the same values. So this is a classical way of implementing an equals method, and you'll find it pretty similar in other programming languages as well. First, check if the type is the same. If so, downcast and compare the values. Otherwise, it's usually not a good idea in most programming to ask an object what its type is. It's considered a rude invasion of encapsulation. Let's have a quick look in IntelliJ at our complex class. It's pretty much as we saw before. There are only a couple of additional methods that we didn't see. For example, here's our hashcode method, and this will ensure that objects that are of the same type will have the same hashcode. There are many other different things that you could do here as well. And we also have implemented a toString method, which is pretty good practice as well in such cases. And then we have a few simple test cases to ensure that complex numbers are working correctly. And running the tests, we can see that everything functions happily. The next design pattern that we're going to look at is full synchronization. In full synchronization, we only have synchronized methods without any waits or notifies. There are some situations in which this may make sense. Let's have a quick look at when we can use this. So the intent of this pattern is to ensure consistency by fully synchronizing all the public methods. Recall that private and protected methods don't need to be synchronized if all the public methods are synchronized, because they can only be accessed from the public methods anyway. As a consequence, if the method is fully synchronized, if the class is fully synchronized, it behaves as a monitor, and at most one method will be running at any point in time. You can apply this if you want to eliminate all possible read-write and write-write conflicts. So read-write conflict is when one thread wants to read the object while another wants to write it, and a write-write conflict if two objects want to write. There's no such thing as a read-read conflict, because if two threads want to read an object at the same time, then there's no conflict. They will read the same value anyway. You also can ensure that all methods will run to completion without having to wait for anything, without having any guards, without any retries, without any infinite loops. How do you apply this? First of all, you simply declare all public methods as synchronized, and be very careful that the state of the object can only be accessed through these methods. There are no public instance variables, except possibly with the caveat of some final, so some immutable instance variables, and no methods that can return references to instance variables. Recall that only methods may be synchronized, and constructors are not considered methods in Java, so they cannot be marked as synchronized If for some reason something weird is going on within your constructors, then you may have to use a synchronized block. This is really pretty much an edge case, so I doubt that you'll ever encounter this in practical programming in Java. But consider the possibility that within a constructor, the constructor passes this to some other object, which might expose the reference to this to other concurrent threads. Well, generally, that's a bad idea, but maybe you have some special reason for doing that, for initializing the object or whatever. But in such a case, then you would probably like to protect that, that bit of code by using a synchronized block. Generally, you should avoid such nasty kind of programming. If you have methods that access static variables, recall that the static variables are shared across all instances of the class, then you have to take special action. So in that case, you shouldn't synchronize with respect to this, because this is going to be different from all of the instances, and each instance will synchronize with respect to itself. And if an object A is synchronized with respect to A, and object B is synchronized with respect to lock B, and they both try to access the static variable, the locks are separate and they'll access that static variable concurrently. The only solution is to have a shared lock, and the idiom in Java to do so would be to grab the object representing the class. So in this case, you would have a synchronized block, which is synchronized with respect to getClass. This is what we see here. This is really very specialized. You won't see that often in Java code, but if you do see it, that's what's going on here. So here within the ... probably a static variable is being accessed, and in order to ensure that we have a common lock for accessing it, we get the object representing the class, so that's guaranteed to be the same lock for all the instances. Yeah, and this is a very specialized situation, but it's something that you might have to watch out for. Furthermore, you want to be sure that every public method leaves the object in a consistent state. Well, this is normally designed by contract. Whenever you leave a public method, you leave it in a consistent state. But be careful. If there are any exceptions that might be raised, and if the program recovers from an exception, you also want to make sure that the object is left in a consistent state. That, in other words, the class invariant holds. So that means if for some reason you might leave through an exception, if the class is the object is in a dirty state, then if execution continues, you may get a bug in your program later on because you're accessing a dirty object. So please be sure if you have any exceptions anywhere, these happen only before any modifications, or if it's after a modification, the object is left in a clean state. If your class has some state-dependent actions, that is, a certain operation should be performed only if the object is in a particular state, probably you don't want to use this design pattern. However, if you do, then you have to rely on what is known as balking. Balking in English means, I don't want to do that. So in coding terms, that means you're going to raise an exception. You can return failure if your precondition fails, if the guard fails, and if the precondition doesn't depend on the state, then you just check this outside of the synchronized code. However, if you want to make sure that clients can be sure that no exception will be raised, then you have to provide the right kind of accessor so that the clients can check beforehand. However, the downside of this is this might lead to some kind of busy waiting. So if you have a design based on balking, we'll see an example in a moment, it might be okay in some situations, but it's probably a bad idea, and you probably want to use the more classical kind of monitor approach using waits and notifies. But we'll see how that works in a moment. Finally, you want to make sure that your methods are short so that you can be sure that they run to completion. Here's an example that we'll see variants of over and over again in the coming weeks. So it's a classical example of an object that requires some kind of synchronization because it has guards. A bounded counter is a counter that counts from some minimum value to some maximum value. So here we have the balking bounded counter, and it implements the bounded counter interface. It has a count variable which can take values from a min value to a max value. We can ask what the value is, we can increment it, and we can decrement it. That's the essence of the counter. So we can go up and we can go down. Clearly, the increment and the decrement methods have preconditions, because I cannot increment if I've already reached the maximum. And similarly, if I'm already at the minimum, I should not be able to decrement. So since this is an example of a class that does have guards and preconditions, so there are methods that can't always be executed, it's probably not a good candidate for applying full synchronization. However, maybe you do want a balking design. You really do want to get exceptions when the object is called in the wrong state. In that case, you can perfectly well go ahead and do what we see here. So here's a balking bounded counter. All the methods are synchronized, value is synchronized, inc is synchronized, and decrement is synchronized. We have a precondition for incrementing. We check that the count has not reached the maximum value, and if it does, instead of doing the classical kind of wait loop, we'll throw an exception. So this is what balking means. Okay, I throw my hands up, I'm going to exit, and it's your problem. And this is perfectly fine design under certain circumstances. We'll see what this leads to, however. One question we'll consider in the discussion is what safety problems would arise if we didn't do any synchronization at all, if we simply eliminated all the synchronized. Another important point that I want to underscore here is you might well say, oh, well, updating a count variable, that's going to be atomic anyway. So why do we need any synchronization? Well, as it turns out in Java, modifying or incrementing an integer value is guaranteed to be atomic, but not incrementing or decrementing a long. So if you have a long integer, then this is not guaranteed by the language specification to be an atomic action. And this is why all the examples in Doug Lee's book that rely on such simple fragments of code, they use these examples of variables which are of type long, because we know that they're not guaranteed to be atomic. Now the downside, as we'll see in a moment, is the client. How does the client know whether it can increment or decrement the counter? The only way it can do that is by sampling the value, which is not ideal. And that means that the client may need to busy wait. So here we have a busy waiting client. What it does is it simply loops trying to perform an action. And if that action succeeds, it will proceed. And if it doesn't, what it will do is it will attempt to, it will busy wait by yielding its thread, letting another thread get in and perform some other actions, and then it'll try again. And this is simply a thinly disguised version of a busy wait. This client can easily starve if there are never any other clients that will change the condition that we're waiting for. Here in IntelliJ, we see the balking bounded counter with the inc and dec methods as before. We also have added an invariant to check that the count never goes outside of the min and max values. So in this case, in our tests, we're going to have 100 clients which are trying to increment the bounded counter, 100 clients that are trying to decrement. All of them should eventually complete and in the end we expect the values of the counters to be 0. And we also expect there to be no errors in our in the invariant. So we will log every time there's an error. Every time our invariant fails, we will log the errors. And quite clearly in this particular case, by running this, we can see that all of the tests run perfectly well. We will, in the discussion section, also have a look at an incorrect implementation of the bounded counter, and we'll see what can go wrong. Here's another example, and this is the example of an expandable array. So in this case, we have an array, a class, which has internally an implementation, has a data variable, which is an array of a certain size. And the idea of our expandable array is that whenever it goes out of range, then we will copy all the values to a new internal array. Here we see the append method. If we go out of range, we're going to increase the size of the array, make it about 50% larger, +1, in case it's initially 0, and we copy all the values. These methods are all fully synchronized, and the only balking happens if there are some errors. So an attempt to index the array out of bounds, or removing the last value from the array if the array is actually empty. Now consider with this array what happens if we want to have sequences of actions that we would like to consider as a single atomic action. For example, I have instances of my expandable array, and I would like to update all of the values of the array to be a particular value. Now, if I have multiple threads trying to do the same thing, I only want these threads to perform these actions as a unit, as an atomic action. So here we have a batch array, which extends our expandable array, and it's adding a new method called updateAll, and this updateAll is synchronized. It loops around and performs an update action, which it gets from a mutator, and it performs that on all of the values of the array. So a question for the discussion for later is, can this introduce some possible liveness issues? Now let's see how we can test this. Here we have a batch array test, and we have two mutator threads for an expandable array of size 20. Actually, the batch array, the extended version of our expandable array. And one mutator thread tries to set all the values to 1, and the other one tries to set all the values to 2. You see them here, setting to 1 or setting to 2 on the batch array. Here's the mutator thread. It's defined with the help of a anonymous inner class. So we create a new mutator with an update method. What the update method does is it's going to try and provoke a race condition. So it's going to do a thread.yield, and then it'll sleep for a random length of time, and then it will return the value which should be used to update. In this particular case, we're actually safe, and we'll see that the result is safe. The reason is that thread.yield will have no effect because we're going to be inside some synchronized code. And even if we yield without having performed a wait, we're retaining the lock on the object. So that means that no other thread can be woken up to get in. We are still retaining the lock on the object, so this yielding has no effect. If, however, we had a broken implementation of the class, then this thread.yield might indeed lead to a race condition. Here we're going to test whether everything works fine. We're going to start our two mutators, T1 and T2, and then we're going to wait for them both to terminate, and then we're going to check that all of the values in the array are equal to the first value. That means either T1 made all the changes and then T2 made all the changes, or T2 made all the changes and then T1. And they didn't interleave, they didn't interfere. If there was any interference, then we would find the array holding a mixed set of values. Here's our expandable array, as we saw before. Here's the subclass, our batch array, which adds the updateAll method, and the updateAll method is synchronized. Here's our batch array test. Here are two mutator threads, which will try to update. They try and provoke a race condition by yielding, but that will have no effect. And then once they've started, we join together and make sure that all the values are the same. And if we run this, everything is fine. Suppose, on the other hand, that we go back here and we break the updateAll method, so it's no longer synchronized. Now, if we run our tests again, as expected, we're going to see there's some kind of a difference here. So at some point, we're expecting the value 2, that's the first value in the array, and there's some value which is different. As with all of these cases, so this time it was, so it's random. This time we expected the value 1 and we found the value 2. The problem with such tests, of course, is that in order to provoke a race condition, you have to play with for example, perhaps the number of threads or the size of the array. And if you pick too small an array size, it may not be that the race condition is provoked all the time. So forcing a program to demonstrate that there's a concurrency problem is always an iffy situation. Now, we see that the error is occurring here. So here we see the different values. And we know that the error has occurred at this location in the code. If we want to see what the actual value is, we can debug this. And what we can do is we can make use of a so-called conditional breakpoint. So this means that we don't want to break always, but we only want to break if we see that something funny has happened. So for example, that BA at location 1 is not equal to BA at position I. And now we'll run this again by debugging it. And now we stop at exactly this point. And here we see the batch array. Its size is 20, and we look at the data values, and in fact we can see it's completely incoherent. So it's a complete mixed bag of values of 1 and 2 because our threads weren't synchronized. And we could see this quite clearly with the help of the conditional breakpoint. So immutability is a fairly useful design pattern, but it's limited to certain situations where we really can cast our design in terms of objects that represent values. Full synchronization can also be useful, but the moment we have a design in which some public methods require some guard conditions, then if a balking design is not appropriate due to forcing clients to do a form of busy waiting, then we'll have to default to the standard approach of the standard monitor idiom offered by Java. Another design pattern, however, which is interesting, is that of partial synchronization. In this particular case, rather than having all the public methods synchronized and having the methods that have preconditions guarded with the classical wait guards, we can partially synchronize the object and restrict the synchronization to just certain critical sections. So the intent here of partial synchronization is to reduce some of the overhead of synchronization by only synchronizing within certain critical sections. This is really an optimization. So lots of design patterns, as we know them, are very special cases. So the classical thing to do is usually what we saw in the second lecture, which is to have a classical Java style monitor, public synchronized methods, have guarded wait conditions at the beginning of any actions with preconditions, perform the action, the mutation, and then perform the notify all for all clients afterwards. So in this particular optimization, we want to reduce the amount of synchronization that's occurring. And you can apply this in particular when objects have both mutable and immutable instance variables. We mentioned this a little bit earlier. In such cases, if methods can be split into a critical section that deals with mutable state and a part that does not. So how would you apply this? First of all, you go to the default solution. You start with fully synchronized methods and then incrementally remove synchronization in situations where it makes sense. Particularly if you have accesses to atomic or immutable values, or if you have methods that don't access any state, then you can remove synchronization there. Also, if you have methods that access mutable state through some other method which is already synchronized, typically another public method, then once again, you don't need the synchronization and you can remove it. Note that you might think that a method that's synchronized calling another synchronized method might lead to a deadlock. That's not the case in Java. So if I have an object X and I have method A and B are both synchronized and A calls B, then that's usually not a problem. The reason is that locks in Java are reentrant. So a reentrant lock is if I have a lock and I say I want to lock this again, then nothing happens. It doesn't lead to a deadlock. It just said, well, you already have that lock. That's fine. As we'll see some lectures from now, there is a particular case in Java where you may get a deadlock, but this is not the situation. So we'll come to that in a few weeks. Now you can replace method synchronization by block synchronization for methods where access to mutable state is restricted to a single critical section. So that means instead of having one large method which is fully synchronized, maybe there's a small part which is just as synchronized, the critical section that needs to be synchronized. So you can reduce the scope of the synchronization. Here's an example. It's a linked list, and the linked list is built up from a number of linked cell instances. The linked cell holds a value, which is a double, so it's not atomic. So doubles and longs are not atomic. And this value is mutable. There's also a pointer to the next cell, but this is final. So once I've created my linked set of cells, the structure is not going to be modified. So I have one mutable variable and one immutable one. Here's the constructor. The constructor simply sets the value and the next pointer. And here we have some of the public methods. First of all, we have the getter. The getter is synchronized. It needs to be synchronized because accesses to doubles are not guaranteed to be atomic. Then we have an updater, a setter, which also needs to be synchronized. And we have the pointer to the next cell. Since that's a final value, it's immutable, we don't need to synchronize it. So here we see a case which is the standard synchronized class mixed with immutability, because here we're accessing only immutable state. A few more methods. Here is a sum method, and the sum method will attempt to compute the sum of this cell and all of the following ones. So if I call sum on the head of the linked list, then it will give me the sum of all of the values in the list. It's defined recursively. So first I pick up the value in this cell. Then I check my next pointer, and if it's not null, then I will add the sum computed by that cell to the value v, and then finally I will return it. So notice the recursion here. Interestingly, there is no synchronized code here. Why is that the case? First of all, value is already synchronized. Next doesn't need to be synchronized. And here, next.sum is the recursive call, and the same logic applies. So as a consequence, this method doesn't need to be synchronized at all. The only synchronization that's needed is through the synchronized accessor. So that's one example of restricting the scope. Or the second example, the first one was the next method, which was completely immutable. And here's another example. So here's the method includes, which checks whether the value x appears anywhere in the rest of the list. So first of all, here we're using a synchronized block to access the value. And if that value is equal to ourselves, then we could return. Notice this is a little bit artificial an example, because I could have simply used the call to the accessor instead of directly accessing the instance variable, because this bit of code is not terribly complex. And there's no real race condition in here. But for illustrative purposes, here I'm using a synchronized block, because otherwise there wouldn't be a synchronized block anywhere here in this code. So that distinguishes it from the example that we had before. Then, so this is the only bit of code where we're accessing some shared resource, and the rest is going to be the recursive call. So that means this part is the critical section and the rest is not, because the rest we're accessing the stateless part, and then we do the recursive call, which is accessing the rest of the list, and that's not part of my state. My state is my value, and the other values are part of other objects which are not part of me. The next example, the next pattern we'll look at is that of containment. Now this is rather different from the ones that we had so far. In the examples, the previous three design patterns were variants of the basic pattern, where we have a classical Java monitor with synchronized public methods and waits and notifies. Here we completely avoid the need for synchronization by making sure that objects are contained in other synchronized objects. So the intent here is to achieve safety by avoiding any shared variables. The unsynchronized objects, which can be complex, are contained inside other objects, and those objects have at most one thread active at a time. So as a consequence, there's no need. You can apply this in a situation if you have no need for shared access to the embedded objects. And these embedded or contained objects, a good way of thinking of them is as exclusively held resources. It's a thing. If you and I are threads, I'm a thread, I have something, I can do something with it. Once I'm done, I can pass it to you, you can do something with it, but then I can't access it. The embedded objects have to be structured as islands, so they're communication closed sets of objects reachable only from a single unique reference. They cannot contain methods that reveal their identities to other objects. So if by some accident you have this object and I can somehow through the back door get an access to it, then suddenly we have two threads again accessing that object. We don't want that. So that's why these objects have to be islands. In particular, the idea is either you have it or I have it. We can't both have it, even parts of it. Some programming languages provide some support for such designs, but Java does not. This means that you would really need to hand check the designs for compliance or make use of some tool that will help you reason about the reachability of accesses to these objects. So you want to be sure that there's no chance that a reference to such an object can leak out so that it suddenly gets exposed to multiple threads, because it's not protected in any other way. It's only protected by its container. You also need to make sure that you can avoid any indefinite postponement or deadlocks in cases where the host objects need to transiently acquire multiple resources. We'll see more about this when we get to the lecture on deadlock. But the key thing is, if I have objects which are protected and they need these resources, suppose they need multiple resources, then they might end up having to wait, and you can get into funky kind of deadlock situations as a result. We're not going to talk about that today, but we'll have a lecture soon where we're going to look in some detail about this whole issue of deadlocks. You now need to design an interface for the outer host object. That host object could be an adapter or a proxy. And you want to make sure that the host is fully synchronized or is in turn a contained object. You could have a hierarchy of objects containing each other. Then you want the instance variables to be unique references to the contained object. So this is the tricky part. You want to make sure that these references cannot leak outside. And that means, for example, if you do need to pass the value of an object, you need to copy it or clone it, so you don't accidentally leak a reference to this thing which only I am supposed to have access to. And you may need to have methods then to duplicate or clone the objects if you do need to pass them outside. In other words, you're modeling these objects as physical resources. So that means if I have it, either I have it or you have it. And if you have it, then you can do something you couldn't do otherwise. If you have it, then nobody else has it. If you give it to somebody else, then you don't have it anymore. If you destroy it, then nobody else ever has it. It's like a thing that you can hold in your hand, but nobody else can have it as well. And if they can be shared, then you have to have a transfer protocol. So you can give it to me, and if you give it to me, then I have it and you don't have it anymore. And there you might want to have a dedicated class to manage the transfer. So here's a simple example illustrating this. This is a minimal transfer protocol class, a resource variable. I don't argue that it's complete. It's just the smallest bit of code that illustrates what you might want to be able to do. So here's a resource variable. It holds a resource of type resource. Here it is. And when I create it initially, the resource is initialized to that value. Now here's the key thing. We might want to exchange it. So the resource, if I want to exchange, if I want to make a resource that I have available to you, between us we'll have the resource variable. So I'll take one of these things that I have and I'll swap it by executing exchange on the resource variable. Now the thing that I had, I don't have it anymore and it's there. And then you can perform exchange and it'll swap whatever you have and then you'll have the thing that I had. Of course, there's more work to be done because when I perform the exchange, I should make sure that I eliminate any access to that I had to that variable before. Otherwise, I could, through the back door, access that variable while you do, and then we have concurrent accesses, which we want to avoid. Here's our resource variable in IntelliJ. Here's the exchange method, which is synchronized. We're going to test this with as follows. So we're going to create two tinker objects. And what the tinker object does, the tinker object is going to have a resource variable that it shares with another tinker object. It will have an integer variable object. The integer variable is simply a data holder which will hold an integer value that you can put or get. And this integer variable is the shared resource. So initially what we're going to do is we're going to grab the int_var object from the resource holder. Then we're going to add our seed value to it. And we have two different seeds. So one Tinker object has the seed 5 and the other has the seed 17. We're going to add it. Then we're going to try and provoke a race condition. So if for some reason the other Tinker object has access to the same integer variable object, then things are going to get messed up here. Then we're going to decrement, and then we're going to check for any interference. So now the value should be 0. But if for some reason we got mixed up and we weren't using the standard private copy of the integer variable object, then we're going to get an error. Then we do an exchange and swap the integer variable that we're holding back so the other thread can grab it. So as you can see, each object is going to work with its own individual copy of integer variables and put them back and forth. So we actually have 3 of them. Each Tinker has one, and there's a shared one. So we're going to be swapping them, updating them, putting them back. If for some reason there was some interference here, then we'll see some strange values. Of course, that can only happen if we have a large number of runs. So here we start a loop of size 50 to try and provoke the race condition. If we run this, then everything is fine. Now here's a bad version of the resource variable that isn't synchronized. So we're going to test that as well. Actually, we're expecting it to fail, so I'm going to remove that now. And now we should see that the failure actually does occur. So here we were expecting a particular value and we got a different one because there was some interleaving of these shared variable and we didn't get unique private access to it, and as a result the whole game is off and we have interference. So notice as well that if we reduce the number of loops here to something much smaller, then there's no guarantee that we'll actually see the race condition. So here, for example, with only 10 loops, everything worked out just fine. And we have to play with this, with the number of iterations to actually see if we can provoke such an error. 50 seems to be the sweet number that actually provokes the race and causes an error to appear. This last little bit is a bit theoretical because I don't have any real running examples, but I'd like to point you to some possible implementations of this. So in this approach called transactional memory, we don't use the basic mechanisms we've seen before, but we use an additional layer which ensures atomicity using additional mechanisms. So the idea of transactional memory is to move the management of the synchronization from the programmer to the runtime. And all you have to do is specify which chunks of code should be executed atomically. Here we see, for example, a hypothetical atomic block. So this says that all of this code must execute atomically. The notion of atomic blocks we know very well from transactions in databases. The idea is to move that concept directly to programming languages. And in fact, there have been many experimental programming languages over the last 40 or 50 years which have introduced such notions. So the idea here is this block of code will execute atomically. Either everything happens or nothing happens. Here's the account example again. We see 2 versions of it. This is with synchronized methods. So we have a synchronized deposit, synchronized withdraw. Here's an incorrect implementation of transferring from one account to another. We first withdraw and then we deposit because it's not synchronized. That could lead to a race condition here. Or this one is also wrong. This is also synchronized. We first withdraw and then we deposit, but this could lead to a possible deadlock. On the other hand, here we have an account defined using the atomic keyword, which doesn't exist in Java, but you could imagine that it might. And here we have a withdraw being atomic and deposit being atomic, and the transfer also being defined as atomic. So if that fails, it will roll back and attempt again. So it's an alternative to lock-based synchronization. It's simpler. You don't lock on an object, you just say atomic. So a transaction is going to be a hunk of code that executes read-write operations on a bit of shared memory, and it's inspired, as I said earlier, by database transactions. In traditional transactions in databases, we have the ACID properties, atomicity, consistency, isolation, and the D is coming from databases. And we leave off the database side because it's not going to be persistent update of the database, but only the volatile memory of our program. But then it's going to be atomic, consistent, and isolated. The idea is that threads are going to be optimistic. So when I have an atomic block, I will start executing. If I discover that there's some error, then I can roll back. I keep a log of changes, and then I can make the changes either permanent with the commit or if there are no conflicts. There are different ways of implementing atomicity, either in software or hardware or a combination of the both. With hardware, we have instructions to start transactions, end transaction, or roll back. And a rollback can undo all of the loads and stores from the beginning of the transaction. Alternatively, an alternative approach is to have a copy of the memory. So what you do then is you make optimistic changes to the memory, and at commit time, you then commit all of that memory, or if you roll back, that means you throw that away and you keep the copy of the memory that you had at the beginning of the transaction. The alternative approach is to have operations which you can do but also undo, in which case the rollback means that every write operation has to be undone in reverse order. You can do this in software as well, but of course it's slower. When can you use this? Well, if you have a job mix that allows it, where you have frequent reads and infrequent writes. This is usually the case in databases. So you have large databases, and each transaction is only operating on a small portion of the very large database. So you can have lots and lots of transactions which are concurrent, and it's very, very rare that two transactions will be trying to access the same part of the database. However, when they do, then you can detect a conflict. In particular, you can compare and see whether the memory has changed since you started the transaction. If it has, then there was a conflict, and you can abort, roll back, and try again. This can be also compared to garbage collection in the following sense. The idea is that with both transactional memory and garbage collection, you have some underlying system which is doing a lot of work for you for managing the transactional memory in the one case, or garbage collection on the other hand, and most of the time it's working without your knowledge. You don't need to care about it, and only in some cases do you need to do some manual management to make sure that the result performs the way you want it to be. Okay, those were all of the patterns that I'd like to show you today. Next week, we'll be moving on to liveness issues. Thanks for your attention.